Hi everyone out there. Welcome to this month's virtual performance chapter for June. Glad to have you join us. And we'll get going here with just a few notes to start off with. My name is Leslie Weed. I'll be hosting today. The virtual performance chapter information is listed on the slide here. Feel free to reach out to us if you would like to speak in the future or are interested in volunteering with us. A little bit about GoToWebinar if you are new to this. In your help screen you will see something that says require assistance, a little hand raiser. If you raise your hand, I will private chat you and try to answer any questions you have that are technical issues with your GoToWebinar. We do suggest maximizing your screen, which you can do that. There's directions there, and also feel free to type your questions at any point in time. We will try to get those questions addressed through each of the segments as Alvin pauses. Also, audio is only available through your computer speakers. There is no dial-in number, just as a reminder. We want to give out a big thanks to our sponsor, SolarWinds, who donates a $100 gift card for us every time. So one of you attendees out there will be receiving a $100 gift card this round. For those of you that are not familiar with SQL Pass, I suggest you look it up and join. It's a free organization. Pass Summit is our big conference that comes around in October. Fabulous, fabulous time. Lots of great sessions, lots of learning, lots of sharing, lots of people to meet. And we have a discount code of VC15LHW9. So if you are registering and need a discount code, feel free to use the virtual performance chapter discount code. All right. Voting for elections is in September, hopefully for those of you that are members. Just a reminder. There are additional volunteer opportunities through PASS, both your local chapters, virtual chapters, and also other various items. So if you are willing to volunteer, it really helps create the community and network we do have within the SQL group. So a little bit of information on where to go look. Okay, so presenting this month is Alvin Chang, and I totally did not spell that on here. Look, I made you change. He is doing index performing, which is absolutely perfect timing for me. So I'm going to make you presenter, Alvin, right now.
Okay. Hold on. Get everything started. Okay, everything look right so far?
Yep, I see your presentation.
Okay, great. Okay, hi everyone. My name is Alvin Chang. I work for a company called Soaring Eagle Consulting. At the front of this presentation, you can see a picture of a book, which is the last book that Jeff Garbus wrote on Microsoft Transact SQL Server, Transact SQL, which is the language that SQL Server uses. That promo image only has Jeff's name on it. I'm actually on the actual book too. So don't ask me how that one worked out, but okay, so indexing for performance. Among the things that we're going to try to discuss in our time frame here is we'll take a look at how query optimization works. We will talk about indexes themselves and how they work with search arguments. We'll talk about the differences between clustered versus non-clustered indexes, as well as how those differences will affect performance. What happens to your queries if you start using OR statements? And we'll also take a look at this concept of index covering, as well as providing some notes about forcing index selection if you think you know better than the optimizer, and sometimes you do, as well as the creation of filtered indexes. Now, in general, SQL Server will use three key techniques in trying to resolve a query. One is a table scan, and A table scan is exactly what it sounds like. It means that it is reading the table from top to bottom, from beginning to end, and trying to find the data that you're looking for. However, with a table scan on a small table, you may not notice the difference, but if you have large tables with lots and lots of rows taking gigabytes upon gigabytes of space in your database, scanning through just one of those tables can be an almost crippling affair. So that's why we also have index searches, and index searches are designed so that when it uses an index, it will reduce the time to bring the data back, or reduce the time to actually locate the data. And then one other additional topic that we will discover is a concept called covered index searches, and we'll bring that up in further detail later on. So, when does SQL Server use a table scan? Well, it uses a table scan pretty much if it has no other choice. Among the possible reasons why it may not be able to have any other choice is you may not have any indexes on your table. And if you don't have any indexes, then the only way that SQL Server has to try and resolve your query is to start from the beginning and scan all the way to the end. As mentioned before, this can be an expensive proposition if this is a really big table. However, if you have indexes, specifically a clustered index, SQL Server will try and use that clustered index at least in place of a full table scan. Now, if you were to try to see if a table scan was actually taking place, well, all you need to do is get a table that has no indexes on it, and then try to run a query against it. And when you run those queries, one of the things that you can do is to run something called show plan, which gives you some hints as to, which gives you some insight, don't want to say hint, as to what the query optimizer is doing to try and resolve your request. And in this case, if we have no indexes and we try to run that query, we'll get some explanation that looks similar to this output, and you'll see that it says it performed a table scan against the database. And you'll also notice that the table scan took 98% of its actual execution time, and the actual location took up only maybe 2%. Oftentimes that 2% may sometimes also include just display. Another way that you can try to check to see if you're actually producing a table scan is to take a look at some statistics information. This is an old school command, so it's not GUI based. You would actually type this at the beginning of your query, and then when you run it, you'll get some additional output that will tell you how much work was done by the SQL Server to read through the data. And you'll see that it says it went to the PTTX table, it scanned it one time. Now, the thing about scan count being 1 usually is a reference to how many times it had to loop through the table. So it only looped through this table one time, and it performed 38 logical reads. Now, you'll also see that there are some references for physical reads and read-ahead reads. Read-ahead reads are basically pre-reads that help increase the performance of getting data off the disk. Physical reads are getting data out of the physical disk, and while they can have a negative impact, the real important number here is the number of logical reads. And in this case, it says 38. 38 in this case refers to the number of pages or number of IOs. If we were to do something similar, to take a look at a query plan, but in this case for an update statement, you can see that we get something similar, although we'll probably see a little bit more information like. In this case, they're updating the PTTX table and they're incrementing the IDs that are already in the table by 1. If we look at the show plan output, we'll see that it's still performing a table scan, but in this case, the table scan is reading the data, and then we'll also see that there's a separate section that describes the actual update, and you'll see that the update doesn't take nearly as much time as just reading the data, which kind of implies what sort of impact scanning through a table actually has. It actually takes more time to read the table than it does to change the data in it. So The next question, index selection. When we try to create indexes, we want to try and create indexes that the SQL Server will actually use. And this typically means that when you design your indexes, they will be designed to resolve a specific query for a specific purpose. But we also have to be careful to make sure that whatever we design doesn't backfire against us, so that creating the indexes doesn't also hurt performance, or it doesn't hurt it significantly. And we'll also have a brief introduction to the idea of index statistics and also usage. Okay, so index selection criteria. During the index selection phase of optimization, there are actually several stages to the execution of a query and optimization of the query, and one of these phases actually is index selection. SQL Server tears apart the query into its components. Some of this is to figure out what tables are involved. Other parts of this process involve figuring out what indexes will help best resolve the query. And it does this mostly by tearing the query apart and looking at its component pieces. Specifically, it'll look at where clauses and join clauses. And when indexes are created, they actually maintain some statistics information that describe the data distribution on the table, and this data distribution information helps us estimate, or helps SQL Server estimate, how many rows are going to be returned based off of a given input or parameter. And using this information, it can actually provide an estimate as to how many page reads are going to be required to get to that data. Now, as we mentioned, one of the things that it will look for where clauses and join clauses. And this is because most of the time, when you are writing a query and it is going to try and use an index, they will directly correspond to anything you stick in those where clauses and join clauses if this is a multi-table query. The kinds of indexes that you can try are ones that will specify a specific value that you're searching for, or indexes that will help you look for ranges of values within boundaries. So for instance, in this example on the screen, we've got where DOB, date of birth, is between a specific range of dates. Something that I should point out about where clauses, while there's just one where clause, most of these composite or more complicated where clauses oftentimes get broken down by SQL Server. So where date of birth between usually gets translated internally to where date of birth is greater than or equal to 3/3/1941 and date of birth is less than or equal to 4/4/65. The key point of this, though, is the where clause is looking at the DOB column. So if we were to try and create an index that looks for information in the DOB column, well, we would probably have to create an index that matches the DOB column. An index may be used if any column of an index matches the SARG. And in this case, at the bottom, we've got a start of an example that says create a unique index on an authors table, and you'll notice there's two columns in it, AUL name and AUF name, standing for author's last name and author's first name. This is pretty much just going to be sort of a phone book type query. The creation of the index, well, we've already seen that syntax, but if we create an index like this, which of the queries that we see below would actually correspond with it? Which one could actually be used? In general, SQL Server will base its index selection on the first column named in the index. So in this case, you've got AUL name, so the author's last name. If we take a look at the queries listed here, you'll see that we've got where author's first name is equal to Jim and the last name is equal to Smith. In this case, we've got both the author's last name and first name with search arguments. The important part is the author's last name is found. And once it finds the author's last name, it can then move ahead into the author's first name. The second query example here with author's first name equal to Jim, because it doesn't actually reference the author's last name at all, means that it is far less likely to take advantage of the index. And there is the possibility that it could use the index, but it is not going to be as good a possibility. If we take a look at this last option, though, where we've got author's last name is equal to Smith and the author's first name is equal to Jim, well, in this case, we've got the author's first name, but the way the query is being written with an OR clause means that it's not going to have, it can find the Smiths fairly easily because Smith is the first name on the index. However, the first name being Jim and the fact that it's OR implies that it doesn't have to be Smith. So it would very likely have to use the index to find all the Smiths, and then it may have to scan the entire table to bring back everyone named Jim just to locate them all. Are there any questions so far?
Nope. Oh, yes.
Okay.
Just one came in.
Yes.
Would you recommend as best practice to create indexes on temp tables?
That is a good question. That really depends on the size of the table. Temp tables, while you can create indexes on them, if they are very small tables, and by very small I mean if they can fit in an 8K page, then there really should not be a need for an index on the table. If they are larger than an 8K page, then having the index can potentially help you. Now granted, sometimes you may not see the index show up in the plans, but if you were to look sometimes at statistics IO output, you may see that running it with the index versus running without the index, the with version actually will use fewer IOs. So it actually is used, although sometimes you don't see it documented through the plans.
Okay. How about when should ascending or descending should be used in index creation?
Good question. Ascending versus descending, it really depends on the types of queries and the orders that you're going to be using your data in. If you are finding that all of your data or all of your, this is going to be in part based on your queries. If you find that 90% of the data that you're searching for is going to be, let's say, at the tail end of a table, or if you're constantly requesting data in descending order, that would make sense to bring the data into the index initially in descending order via the index.
Okay. We have
Any questions?
Yeah, we have quite a few that came in. Let's go ahead and do one more.
Okay.
So for a unique index, SQL
Yes.
could use it as a subset of the data the columns cover the predicates, but it doesn't always do that?
If the well, can we hold off on that particular question simply
Yep.
because we've got a section on covering indexes coming up.
Oh, perfect. Okay.
All right.
How about what could you do to improve the OR section of the query? Would you just create a different ordered index?
Also a good question. If you've got OR sections of queries, what you can do is you can try to create multiple indexes, and this is really something that you have to test on your own for your particular situation. But if you have different kinds of ORs, and by this I'm talking about column A equals this or column B equals that, then you would generally need multiple indexes to resolve it, in which case the internal resolution starts to look really similar to a union clause, to a union statement. If you are dealing with OR clauses and they're all looking at the same column, then there really isn't that much that you can do except make sure that you've got the right index selected and the right type of index. And in this case, if the right type, I'm talking about possibly covering the index for additional performance. If you have lots of ORs with lots of rows coming back, if it's a non-clustered index, that can affect your performance if not all the columns are in the index and you're constantly going back to the base table to bring data back. Any other questions?
Yeah, so any difference between creating index on a temp table right after its declaration or right after it gets populated?
I recommend doing it after it's populated. The simple issue is if the index is created while the table is still empty, the statistics that are generated for the table, for the index, are based on the current state of the table. And those statistics do not automatically update. So, or don't automatically update unless you have certain features turned on, and even that's based off of an algorithm when it does the update statistics. So if you populate the table, then create the index, what will then happen is the index will perform statistics measurements, and if it's a clustered index, will sort the data as part of the process. If you create the index prior to it, and let's say it's a clustered, you'll actually make the inserts into the table slower, and you won't have any statistics gathered. Okay, I think we should move forward at this point.
Yep.
Okay, so moving ahead, index selection, review of the general index types and optimizer selection criteria. We'll also talk about when indexes can slow access and statistics and usage. So, in general, we've got 3 different kinds of indexes in SQL Server. There are clustered, there are non-clustered, and full text. We're not going to cover full text in this seminar. You're allowed 1 clustered index per table, and the note that's always made about clustered indexes is that the clustered indexes are directly connected to your table. So when you create a clustered index, it sorts the data into your clustered index order. For non-clustered indexes, you're allowed 999 non-clustered indexes per table. Not that I ever recommend getting that high. The old limit was 248. I don't recommend that one either. And as an FYI, that limit of 248 ended with SQL Server 2012. That's when the 999 limit came about. The key difference between the clustered versus the non-clustered is, as I said before, clusters, the data actually becomes part of the index and is the final level of the index, whereas non-clustered indexes just maintain a series of pointers to the individual rows. This is sort of a graphical representation of a clustered index so that we can get an idea as to how the internal structures kind of look. It's not an exact representation, but it gets the idea across. So for a clustered index, and let's say that we're talking about, in this case, last names. So we'll use the telephone book as an example. If you create a clustered index, say, on people's last names, what will happen is it'll create a B-tree structure, and the B-tree structure is going to be our search structure. And for those who are not familiar with B-trees, all they are binary search structures. So what you say is something greater than or less than. If it's greater than a value, I will go in one direction. If it's less than a value, I'll go in a different direction. And because the B-tree allows, the reason why B-trees are used is because they allow searches to take place in a relative constant number of moves. In this case, if we have a B-tree for a clustered index, the root page is the very top of that tree, the beginning. And you'll see that it has a breakdown of last names. And you'll see that it's got Albert, Jones, Mason, and Quincy. This is a distribution of the last names so that we have additional pages that allow us to drill down into further detail. And if we were to search for, let's say, Exeter or Houston, then it would check Albert and then Jones, and if Houston is greater than if it is greater than Albert but less than Jones, it will follow the Albert pointer on the tree and then start looking to see if it can locate Houston. So the point being, we have this root page at the top, and as we follow this search tree, figuring out which one's greater or less than that we're looking for, it'll eventually get us to this point where we get to the data page. And because it's a clustered index, it is the table itself. And once it gets to the table, it can locate the row that you're looking for, or if you're searching for a range of data, it can start scanning through the table as well. The non-clustered looks suspiciously similar. However, it's got this intermediate, you'll notice that we've got this intermediate page, and then we also have a leaf page thrown in between it and the data pages. And what you'll find is that because you can only sort the data one time via the clustered index, when you create a non-clustered index, this additional layer, the leaf page, pretty much contains the entire sorted list of everything that you're looking for. And that list then contains pointers to all the different data pages that match what you've indexed on. So in this case, if we've got first names rather than last names, you'll see that we can follow the names of the first names through the root page down to the intermediate page, but then when we get to the leaf page, you'll see that, well, if we start just with Amy, you'll see that there's Amy. You can follow it to the intermediate page and then down to the leaf page. We can have lots of Amy's in a phone book. And you'll start seeing that there's Amy, and then you may find hundreds of additional Amy's. And each one of these Amy's will have a row pointer to the data page so that it can find the actual data for that particular Amy. Now this means that if there are, let's say, 50,000 Amy's in the phone book, then you'll find leaf pages that have up to 50,000 rows worth of Amy's and 50,000 pointers to the various Amy's that exist in the phone book. Now, because the non-clustered index has that additional layer, in general, the clustered index is just a little bit faster. In general, the clustered index tends to be that 1 IO faster because it does not have that additional layer. Clustered indexes are also good for retrieving ranges of data, and this is simply because it sorts the data. And if your clustered index is keyed off of the column that you're searching on, and it puts all that data in sorted order, then you can, let's say for last names, everyone named Smith may be located fairly quickly because it only needs to find the first person named Smith. And then when it locates that first row, because it's in sorted order, the next person named Smith will immediately follow it. When you're dealing with indexes that are for ranges of data and also for queries that use order bys, clustered indexes tend to work really, really well. Non-clustered indexes, as I said, tend to be a little bit slower. They also take up more disk space, but they're oftentimes better and faster than trying to table scan. Now, you'll also notice I said oftentimes. There are situations where using a non-clustered index to resolve a query may actually take so much more additional time that it will actually cause SQL Server to say, yeah, let's not use the non-clustered index, let's table scan it anyway. Okay, some notes about clustered indexes. One note about clustered indexes that some people fail to realize, when you create a clustered index, it is actually creating a duplicate copy of your data as part of the process. And as such, you're going to need to free up about 120 to 130% of the size of the current table in order to make enough space. Another recommendation is always have a clustered index on all of your tables. Now, this comes with a caveat, because there are lots of people who get taught that you need to have a clustered index and it needs to be on the primary key, and the primary key should be an integer. Need to have a clustered index is absolutely yes, it's a good thing. Does it have to be on the primary key? That depends. The primary key is not always the best choice, because you may not always be searching on the primary key. And does it always need to be an integer? The integer is a nice value, but in the same sense, it may not be the best way to search for the values that you're looking for. So what sort of indications should you use when deciding? Clustered index indications. If you are searching for ranges of values, ranges of, let's say, names, or ranges of integers, or ranges of dates, these things can be placed in a clustered index, which allows them to be sorted and oftentimes will increase the performance of bringing that sorted data back. Sequentially accessed columns. If you're dealing with columns of data that are constantly, actually I'm not certain exactly what that one means. All right, column joins, other than the primary key. If you were joining tables and the key columns that you're using to join your tables, let's say 60 to 70% of the time in your queries, chances are they may also be good candidates for clustered indexes. One other thing is static columns. This basically means that the column itself that you put in the clustered index doesn't change a lot. And there is a reason for that. You know how I said for the non-clustered indexes, if they're the last level is actually the leaf level and it has pointers to the data pages. Well, if the data pages are sorted by the clustered index, what happens if you change the data in the clustered index? Well, then the order and the position of that clustered key data moves. And if it moves, it means all those pointers are going to be bad, which means that SQL Server has to update all those pointers. And that can increase what we refer to as overhead of maintaining lots and lots of indexes. Okay, some other notes about indexes, now going on to non-clustered. Non-clustered index selection tends to be most effective if you are bringing back as little data as possible. The note here is that it is more effective if less than 20% of the data is selected. The note that Jeff provides here is that it's actually closer to 5%, and he has some stories as to why that may be the case. But in general, if you're bringing back lots of data back from a non-clustered index, you can actually hurt performance. And actually, the more data you bring back from a clustered index, the closer you will get to a SQL Server saying, I'm going to perform a table scan instead. Now, non-clustered index can still do things like help with sorts, joins, and group by clauses. However, oftentimes this is sort of a second chance effort simply because the query, the indexes have already been created for the clustered index, and so that option is no longer available to you. Non-clustered indexes are also the types of indexes that are used primarily for index covering, which we will get to. Okay, now there are some limitations. Now I've updated this slide specifically for 2012 and higher. You are allowed a maximum of 32 columns, and of those 32 columns, only 900 bytes of index width will be allowed. With 900 bytes of index, it is very easy to create an index on a varchar 1000 column in SQL Server, and if you try to do that, you may get a warning When you create the index, that will tell you that the index exceeds the maximum byte count and that the index data may be truncated. And you may also end up with runtime errors if you try to search off of these indexes and it's not specific enough. For non-clustered indexes, the byte width is 1700 bytes, and I also provide a note that 900 bytes for both if you're working with any versions of SQL Server that are older than 2012. Okay, so as mentioned, primary key is not necessarily the best choice when considering clustering versus non-clustering. And the key reasons behind this are a primary key is a logical concept, it's not a physical concept. However, indexes are physical and not logical. And while the two are definitely related to each other, the key thing behind the key issue with a primary key is that you are trying to make sure that you are enforcing uniqueness. And when you are dealing with a clustered index, you are not concerned you're less concerned with enforcing uniqueness and more concerned with, for the index, its efficiency at retrieving the data that you're looking for, and also helping to define relationships. So when you're defining a primary key, what you're really concerned with is whether or not the primary key has duplicates. Well, you can do the same thing with a non-clustered index, you just have to define it as unique. When you're creating a primary key, the enforcement mechanism that it uses is a unique clustered index. You don't need to necessarily make it clustered. And there are ways in the code for creating a primary key where you can say, make it a non-clustered index. Okay, now there are things that you can do to try and prevent yourself from hitting that 1700 or 900 byte limit, and this one thing is incredibly useful. It's called include. Beginning in SQL Server 2005, they added this idea of the include column. If you have large multi-column indexes, you don't have, and you are not searching off of all the columns, but you do need to have that column data in the index itself. You can place those columns in the include column rather than on the index key. This way, these additional columns that you're not searching on, but you may be using as part of the select statement, can be part of the index, but not part of the key, part of the search area of the index. So it will still be able to find the data very quickly, but then when it gets to this last area, the leaf pages will have all of these additional included columns in it so that you can use that data as part of your select without necessarily having to head over to the data pages themselves. And with that, we actually start talking about this idea of covering indexes. A covering index, and I'm not going to move to the next slide at this point, a covering index is pretty much an index that has been created with all the columns required for the query built into it. Why would you do that? Because sometimes going back to the table takes too many operations or too many I/O operations. Way back earlier in this presentation, I used this idea that we may have 50,000 AMIs and that the leaf page will have 50,000 rows. Well, to get data about each one of these AMIs that is not in the leaf page, you have to do a read for each one of those 50,000 rows. This means that you're going to have to do 50,000 IOs to get all the data for all of the AMIs from the index. If you get all of that additional information, but if you don't need all the information from the data page and you just need, let's say, Amy's middle name, then you can put, or, let's say, no, forget middle name. Let's use phone number. If we get Amy's phone number put into the leaf page, then instead of having to go to the data page to get the phone number for each of the 50,000 Amy's, it will get to the leaf page and find Amy and the phone number, and then the next Amy and the next phone number. Without having to go to the data page to do 50,000 additional IOs, it just starts walking down the rows in the leaf pages. This is what we mean by index covering. So we're writing the index or creating the index in such a fashion that all the columns you need are in the index so that SQL Server doesn't have to do that last step of moving from the leaf to the data page to cut down on time. There is a caveat to this though. Whenever you create an index like this, you are effectively duplicating the data. So there are now 2 copies of all the Amy's and all of Amy's phone numbers, except it's not just for Amy, it's for everyone in the database. Okay, questions? Hello?
Sorry, yes.
Yeah.
Creating a non-clustered index, whether online or offline operation.
In general, you should be able to create a non-clustered index. In general, non-clustered index tend to be a more online operation than an offline one, in part because it is effectively scanning the data, but doesn't lock the entire table like, say, a clustered index creation does. So it shouldn't make too much difference, but if it does, and quite frankly, most of the time when it does, it's on this last step when it's trying to put the index in place. I would say do it as online if you can, just to be safe.
Okay. For column store indexes, what's the difference between them from clustered and or non-clustered indexes?
I don't want to get into column store indexes, not for this particular presentation.
Yep. Okay, that sounds good. So we'll put that off. What is the recommendation in search functionality where we could have multiple search criteria and need to perform OR conditions? Is dynamic SQL recommended at all here?
I'm having trouble understanding the question.
Yeah, I'm not quite sure either. How about fill factor?
Okay, well, fill factor, what you have with fill factor is how much data is required to, quote unquote, fill up a page before SQL Server says the page is full enough and we need to move on to another page. The idea behind fill factor is that one of the tasks that can occur internally to an index is if the data is coming into the index out of order and the index or the data pages are already full, so there's no room to put any more data into the page. Well, this means that SQL Server now has to kind of stop the operation and split the page apart. It'll put half the data in one page, half the data in another page, and restructure the index accordingly. That's called a page split. Now, because SQL Server has to stop the operation and do this intermediate task, this can make inserting into the table a slower operation than it needs to be. So in an effort to try and reduce that tendency, you can define a fill factor that says, let's say, a fill factor that forces SQL Server to say the page is full at, let's say, 75%, which means 25% of the page is actually empty, and if it needs to, it can add some additional data to the page when it needs to without forcing the page split. This reduces the number of page splits, but it also means that the number of pages in your index gets a lot larger, which means that the number of IOs required to read some data out of the index is not quite efficient because it takes more reads to get through it. And also the index will take more space. So it's a useful tool, but it can come back and haunt you in the end. I have had clients that have, tried to reduce page splitting because it was hurting their performance, and then what would happen is 9 months down the road, they find that their disk space filled up incredibly, and it's because they set a fill factor that was so large that they weren't filling in the pages as efficiently as they could have, and we ended up having to reduce that.
Interesting. Okay, here's a really good question. If you create a clustered index with first and last name and have a query searching for first name and address, would you need to create a non-clustered index for first name and address, or just address, since the first name is brought along with the clustered index? So where would you put address, basically?
Okay, if it's the clustered index.
So the clustered index has first and last name, like your first example.
Okay. Oh, the clustered index had last name and first name. The order is important.
Okay, yes. So then if they were to search, if they were searching by, let's just say, last name and address.
Yes.
Where,
okay. Then if they were searching by last name and address, then they wouldn't, and it's the clustered index, then they wouldn't really need to add anything, because it would find the first instance of the last name, and then it's at that last name for the rest of the table, and then it would start performing what's called an index scan. It uses the index to locate the data and then scans the rest of the way down.
Okay. And then if they wanted to do it by first name and address, would you do an additional index?
Good question. That depends on how many rows you're trying to bring back. Okay. It depends on A, how many rows you're trying to bring back, and B, are you going to put the address in the index?
Right. Okay.
Because if you were to try and put just the first name into the index, and let's say you were looking for everyone named Jeff. Well, if this is the phone book, you may have 50, 60,000 Jeffs in the phone book. There is a point of diminishing returns in SQL Server that I've mentioned. The more data you need to bring back from a non-clustered index, the closer you get to the table scan. So if bringing back if you were only going to bring back one Jeff and their address, the non-clustered index would work. But if you were going after, let's say, 50,000 of them, then you may reach a point where SQL Server just does the table scan.
Okay. So here's an interesting question. How are similar values sorted in a non-unique clustered index? And this makes me think of null values when you ask this question, so this is a good one.
How are similar
values sorted in a non-unique clustered index?
Similar values in a non-unique. They are pretty much, as far as I know, they're pretty much in a heap order. It's the order that the index gets them in. That can vary depending on how SQL Server chose to create the index. Sometimes if you're dealing with a single-threaded index creation process, everything will be sorted in one step, and it's based on how SQL Server sees the data as it comes in, as it went into the table. Other times, SQL Server may use a threaded process, so you've got 2 or 3 or 4 up to 12 maybe threads trying to create the index, and at that point you may see the data scrambled. Now that is if it's not key data. If it's key, well, no, even if it is key data, because we're talking about, it's the same issue as with the non-clustered index in relation to the AMIs. The AMIs will exist in the table and in the order that, the AMIs will exist in the index in the order that they were found by the index creation process. And that can vary depending on how the index was created, whether it's single-threaded or multi-threaded.
Yep.
Did that answer the question?
I believe so.
Okay. Okay, do we want to move forward?
I believe so. Thank you.
Okay. Okay. So, Right, so optimizer selection criteria. During index selection phase, the optimizer will determine which, if any, indexes will best resolve the query. It'll identify which indexes match the clauses, and then estimate the number of rows that are going to be returned and estimate the number of page reads. So, and as a note, this presentation is actually based off of one of our classes, and in the interest of time, I'm going to move us past this, because I want to get to let's see, the difference between utilization of two following indexes. Okay. Some issues that I wanted to discuss about indexes and well, whether or not if you have two similar indexes. One of the issues that I tend to run into in my consulting practice is that people sometimes tend to overdo it on the indexes. Jeff actually tells a story where he went into a client site and found that they were complaining about performance and they had 150 indexes on one table and were wondering why their inserts were taking 5 minutes to complete. One of the things that people should be aware of is that indexes require maintenance, whether that maintenance is due to our own action or that maintenance is required as part of our regular performance maintenance on the server. If we change data in the indexes, it is not an isolated thing to the other indexes. This also means that the more indexes that you have, the greater you can affect performance. If you have data that exists in a table that doesn't change, then you can have as many indexes that you want, and that should make no difference because the data doesn't change. But if you start changing the data, there is overhead related to the changing of the data. The other issue is if you have lots and lots of indexes, you are duplicating the data many times. I did run into at least one client that had a table that was effectively 1 gigabyte. And yet this 1 gigabyte table, while not terribly large, had 50 gigabytes worth of index on it. And they had to start questioning me as to why the table itself was so large and taking so much time to maintain, because it wasn't terribly large, but they made so many copies of the data that it became unwieldy. Now, these were just the indexes. There also is a concept in SQL Server called an indexed view, and views don't have any real physical structure because they are queries that have been defined and you can treat them like tables. But if you create an indexed view, SQL Server has to maintain the index for that view, and that suddenly makes the structure physical and starts creating additional copies. Which leads me to my recommendation: if you try using index views, be very, very careful. Now, in this particular example on the screen, we've got two indexes and we've got a price column, and you'll notice that there's two indexes, price and royalty, and then price. If we take a look at the query, which one actually is the better choice? From my perspective, the price and royalty column, price and royalty index, covers the entire query and is more likely to be chosen. The issue that I'll bring up, though, is that if you have price and royalty, do you really need the price index by itself anymore? And chances are, if royalty is a really small column, you probably don't. And this is my warning. If you've got lots of indexes, start looking for redundancies. If you've got 27, if you've got 10 indexes and you think that's too many and you want to bring it down to, let's say, 8, start looking for indexes that start with the same column. If they start with the same column, then technically they should be able to function the same. If they have lots of additional columns following that key, they may perform slightly slower, but you may get some of that performance back from the fact that, well, you're not trying to maintain 10 indexes, you may be trying to maintain only 8 or 6, something smaller. Any questions?
So we do have one.
Yeah.
At times, index recommendation tools will recommend a non-clustered index which contains all other columns that are not part of the non-clustered index key fields. In
And I'm
index,
about to interrupt and say, gee, you noticed that, huh? But,
an index of the size will be as large as the table itself, but do these still make sense in some situations?
what I find is if it becomes as big as the index itself, oftentimes no, because if you've hit that stage, chances are you may need to reconsider what your clustered index is. Because if you're trying to bring back that much information, you might as well have scanned the table anyway.
Okay. And this one is slightly column store. I'll let you choose whether you want to answer this. What kind of row or pointer does a non-clustered primary key have on a clustered column store table?
And we're going back to the column stores. I don't have quite I don't have quite as much depth on the column store indexes to sufficiently answer that one.
Yeah, and that's kind of interesting. Kind of goes both ways. Okay. How about what happens if we create a non-clustered index on a column where we have more writes? Will that make writes slower?
If you have a non-clustered index on a column and you're updating it, it will slow the non-clustered index updates a bit, but it's nothing compared to a clustered, because what happens with a clustered is if you're changing, let's say, a clustered index, not only is the non-clustered index changing, but it's changing the position, forcing the clustered indexes get changed, and all the non-clusters that point to it have to get changed too. So comparatively, updating information that affects a non-clustered index, while it has an impact, isn't as great as if you're modifying that for a clustered.
Okay, perfect. So,
Any other questions?
So we have 3 minutes left. Was there anything else you wanted to cover?
Okay, let's see. Well, this actually got us to the point where we got to the actual index covering, which I kind of already discussed.
Okay. Also, for slides, do you have a blog or link for your slides, or can we upload them to the chapter site for people?
I can provide a copy of it to you, or they can email, let's see, I believe, no, there is something I can discuss for the next 3 minutes.
Okay.
Index selection, forcing index selection. Every now and then we have, well, it's more common than people think it is. People think that they create an index and think that the SQL Server optimizer should be choosing it. The optimizer tends to get better year after year, version after version, with every release of SQL Server. People always wonder, well, if it doesn't work the way I want to, how can I force the index selection? And it is possible to do it, although I'll also warn you, don't, and there are good reasons for it. The following is the example of how you would actually force an index within a query. You'll notice that when the table is listed in the query, it'll actually specify an index with the index name. That's generally how you would force an actual index selection. Now, why wouldn't you want to do this? In general, SQL Server is making decisions on index selection based on the data that it has collected about the data in your tables. If that information is stale or not at a fine enough resolution, SQL Server can make the wrong choice. But the problem is your data can change over time, and sometimes the index that you chose 6 months ago to fix a slow-performing query problem may not be the right solution down the line, at which point you'll suddenly start to see performance failing, and you'll see that it's using an index, but it may no longer be the right index choice based on the data in the SQL Server. So my recommendation is, before you start trying to do forced index selection, explore your options on update statistics, the sampling numbers for your update statistics. Sometimes you may even need to run update statistics more often, and sometimes it may even be the queries that you've written. And we actually do have courses specifically geared to writing better SQL code to try to avoid some of these issues. Is it 100%? No. But in general, I don't recommend the use of forced indexes. Okay, now as the last thing that I can present is, and this is from Jeff's slide, we actually do provide versions of this presentation on YouTube. And we also can provide this particular presentation in its PowerPoint form.
Okay, fantastic.
Yeah. So.
Super.
And I'm not certain how Jeff normally does it, but.
Okay. Alvin, thank you so much for joining us. Attendees, thank you. We'll see you next month for the performance chapter presentation. I'm going to go ahead and stop the recording now. Please look at the chapter website in the future for the copy of this recording and also the slide deck. Thank you. Have a good day, Alvin. Thanks so much.
Bye.